Let us look at proposition number 51 of book 10 of Euclid's Elements. The proposition says to find the fourth binomial straight line. So, what's a fourth binomial straight line? The definition says if the square on the greater term is greater than the square on the lesser by the square on a straight line incommensurable in length with the greater, then if the greater term is commensurable in length with the rational straight line set out, let the whole be called a fourth binomial. So let's see how we can find this fourth binomial straight line. And in the process, we will understand this definition in a much better manner. Set out numbers AC and BC. So let's set it out. So AC and BC such that AB is to AC is not having a corresponding number square is to number square ratio. And AB is to BC also does not have a number square is to number square ratio. Set out a rational straight line D. So let's do that. Now let EF be commensurable in length with D. So EF is not there as of now. So we have to construct EF so that it is commensurable in length with D. EF. Now since D is a rational straight line, so which means D is rational, and since EF is a magnitude which is commensurable with D, therefore EF is also rational. Okay, let AB is to AC. AB is to AC is equal to EF square is to FG square. Again, we don't have a FG square, but we have AB, AC and EF. So we can get the square of that. So we have to find FG square. Again, we know how to do that. Here, EF square is to FG square is equal to a number is to number. Why? Because AB and AC are numbers. And AB is to AC is equal to EF square is to FG square. What this means is that EF square is commensurable with FG square. And since EF is rational, that means EF square is rational, which means since EF square is commensurable with FG square, it means FG is also rational. EF square is to FG square does not have a corresponding number square is to number square ratio. Why? Because again, because of this proportionality, AB is to AC does not have a number square is to number square. So that means EF square is to FG square also does not have a number square is to number square. What this means is that EF is incommensurable in length with FG. So we have shown that EF and FG are rational straight lines commensurable in square only. So EG is binomial, where EG is nothing but EF plus FG. AB is greater than AC, right? Because AB is the sum of AC and BC. So AB is greater than AC, which basically implies that EF square is also greater than FG square. Let FG square plus H square equal to EF square. Again, we don't have H square, but we know EF square is greater than FG square. So we find H so that it is when summed with FG square gives us EF square. Let's look at this proportionality again. AB is to AC is equal to EF square is to FG square. Now we do conversion of this proportion. So in conversion, AB is to the excess, that is BC, is equal to EF square is to the excess, that is H square. Again, AB is to BC does not have a number square is to number square, which means EF square is to H square also does not have a number square is to number square ratio, which means EF is incommensurable in length with H. We can write this in a slightly different way by saying EF square is greater than FG square by H square, where H square is incommensurable with EF. So what have we achieved? We have EF and FG are rational straight lines such that EF and FG are commensurable in square only. EF is commensurable in length with D. So that means EG, which is the sum of EF and FG, is a fourth binomial straight line. So now let's go back to our definition. If the square on the greater term, now here EG is the fourth binomial. So let's look at EG, which is divided into its terms at F. So if the square on the greater term, EF square, is greater than the square on the lesser by the square on a straight line incommensurable in length with the rational straight line set out, that is D. Here, if H square is incommensurable with EF and EF is commensurable with D, that means H square is also incommensurable with D. Let the whole be called a fourth binomial. So that is proposition number 51 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.